Okay, but at least it is done. So let's get started with this lecture. Second, so today we'll basically take a deeper dive into flip-flops essentially, but we'll see its practical application in certain circuits. So hopefully it will be easier for us to grasp based on our understanding so far of flip-flops characteristics, all right? So without further ado, let's get started. First, we will talk about registers. I already told you that registers are essentially a bunch of flip-flops working together. One flip-flop can hold on to just one bit of information, but if you need to handle, say, 8-bit numbers, 16-bit numbers, 32-bit numbers at a time, you have a group of flip-flops and you call them a register. So like 8 flip-flops working together is a register of 8-bit. Okay. So here is an example of how a register can handle data, how you load a specific data into a register, save it, or clear it. Okay. You can read this description at home, but I'm going to zoom into the circuit and explain its functionality. All right. So first, can you recognize this block? Now, this is a flip-flop essentially. How do you know it's a D flip-flop? Basically, we use D as a node name to represent it as a D flip-flop. And D flip-flops are simple because it is just going to send the data to the output. Essentially, there is no toggle, set, reset, JK, other complicated stuff. Just send the data to the output when the clock edge appears. Now, notice there is a line that has been marked as clear. So basically, we are trying to create a feature for this flip-flop where you apply a certain input and all the output will be cleared. By cleared, I mean will be 0. Remember, we have seen a few types of flip-flops, JK flip-flop, SR flip-flop, T flip-flop, D flip-flop, right? A few versions. And people have other variants with additional features. For example, hey, I just want to add a clear feature. I don't need any other feature. I just want to add a clear feature to D flip-flop. You can do it. So this is a flip-flop where you have an additional clear feature. Sure, it can send that data to the output when the clock edge appears. But if you want, you can always clear the output at any given time using this additional signal. Okay? So obviously, we cannot cover every version and variants of flip-flops. We didn't cover everything. Depending on the need, you can always customize your existing flip-flop. The types we covered, they are essentially foundational to any kind of sequential logic. You can always add some component here and there to add extra features. Okay. So I hope that makes sense, right? For if you want to get everything cleared out, maybe if you want to reset your register to 0000, just activate the clear input and it will reset everything to 0000. All right. Typically, registers need to be reset every once in a while. So we need this input. Okay. Now, next. This is your clock signal, as you see. This is a clock input. We have done a little bit of a trick here. Instead of just directly providing the clock input, we have coupled it with another signal called load. So, we are naming them in a way that it makes sense. Its functionality can immediately make sense. So we are deciding whether to load the data. And what do I mean by the data? The data that you're providing here. So notice that you are providing a bit stream. And for this particular example, it is 1101. We're trying to copy 1101 to this register. How do you know that your data has been copied? You control the D input, but you don't control the output. As long as your data is sent to the output, it will be saved, right? That as long as you don't change the input again. So you are trying to send this input to the output essentially at the clock edge, by the way. But imagine if you keep your load signal to be 0, and this is an AND gate, your clock, no matter what, if it is 0 or 1, doesn't matter, the output will always be 0 because it's an AND gate. So you'll never have a clock activation, so nothing will happen. So essentially, this load signal, although interesting, the fact is, on chip, the clock is always oscillating. You cannot stop the clock. It is shared with so many different components. It is always oscillating. How can you kill the clock for a specific register? without killing it for the entire chip. This is a simple example, easy to explain example. For this particular register, take the clock input, but don't provide it directly. Use an additional gate and merge it with an additional control signal. Now, this control signal will essentially control the practical clock that this register gets. Does that make sense, folks? So remember, this clock signal is a very important and very big signal channel that is routed across thousands, if not millions of components. So you don't just turn off the clock, but you can turn off the clock effectively in certain sections using this type of trick. And to be honest, this is honestly never used. This approach that I showed you, it is never used because there are some problems, but it is so easy to explain at this level. I chose, and the textbook chose to talk about it. But practically, there are some issues. I can talk about the issues, but I'm not, I don't want to take a random tangent here today. So this works logically, but there are some practical challenges. So that means there are better ways of incorporating this additional control signal. There are better ways, which you are not seeing here. In 433, you will see some of them. Okay. Now, the point is, once I set load equals 1, then it's as if your clock signal is basically the controller now. Because 1, if you have clock 0, you get 0. If you have clock 1, you get 1. Essentially, you get the clock signal at the output, right? You see my point here? So once you decide to load, you essentially start putting in the clock to the flip-flops. So once the flip-flop gets the clock edges, it will send this input to the output, okay? So this basically represents a transition from 0 to 1. So the reason why you see everything was 0 before, that represents your register was cleared. So it was cleared. And now, once you're ready to load, you set the data at the D flip-flop inputs, and then just provide a clock edge, and it will be loaded. You see my point here? It's like pressing a button and loading it in. By activating the clock, you load the data. And once it is loaded, as long as you don't enable the load signal, how can you keep the data safe now? My other question, right? How can you make sure that it is not overridden anymore? Just change your load signal to 0. So for the next clock edge, you don't have any other activity. Even if you change your inputs, your outputs don't change. Are you good so far? Okay, it's a simple concept. And we're getting to more complicated examples soon. So this is a very simple example of how to load, clear, and clock a register. Okay. In this example, you looked at 4 bits, right? I deliberately chose to talk about 4 bits without any loss of generality. If I want to make it 8 bits, just continue. 16 bits, continue. Just repeat of the same thing. Now, we will take a step up and start considering registers as blocks. So now what you're looking at here is, by the way, here in this slide, we'll talk about data transfer between registers, okay? In the previous slide, you saw how to save a specific data in a register. But now how about I copy a data, given set of data, from one register to the other? How can I do it? Using the components that you've learned so far. Let's talk about it. So here, A1 and A2. See that? And B1 and B2. So basically, A1 and A2 are flip-flops. That's why it's mentioned here. It is a simplified symbol. We are not showing D, clock, blah, 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 nothing. Just to make it simpler. And by the way, these are taken from textbook. Okay, so I didn't decide to make it simple like this. The textbook did. So, okay, so this is a flip-flop. This is another flip-flop. And this is a register. So it is a register with 2 bits. Just to keep it easy for us to explain and help us fit that in a slide, right? It could always be like 16 bits, doesn't matter. Same thing. So we are looking at a 2-bit register, and this is another 2-bit register. So you have 2 registers, register A and register B. And I have another register right here, which is say register Q, and we are trying to copy A or B in that register Q, selectively. So I should be able to control which one to copy to Q. Okay, so here is how this is basically trying to teach you how different components that you have learned about so far can come together and achieve something practical. Okay, first, imagine I'm trying to send register A's information to Q. Here is how we do it. To selectively choose a register, we need tri-state buffer. Remember tri-state buffers, folks? Did you have a lecture on that? Okay. If you don't remember, if you don't have it on top of your head, it's fine. But please review them. You'll need it for the final exam. So this is a tri-state buffer. You have an enable signal. Once you provide enable equals 1, then it sends the input to the output. So it's kind of like a bridge, but it's a control bridge. Once you enable it, it lets the input to the output. So you have an enable signal for the tri-state buffer. First, imagine you set enable equals 1. So this tri-state buffer gets 1. The other tri-state buffer gets 1 as well. So these two tri-state buffers are activated. However, notice you take an inverted version of the enable and provide it to the other tri-state buffers for B. So the output of the B flip-flops will be decoupled from the bus. So it's no longer going to change anything. So the only thing that is connected to the bus now is the output for A. And now once you have the clock edge, it's not shown here. By the way, it is shown for the output flip-flops. Notice, once you provide the clock edge, it will take this and send it to the output. Okay, let me clear it up a little bit. So imagine you have the output for this flip-flop here because the tri-state buffer was activated, but these are deactivated. Now, okay, do you recognize this load and clock signal now, folks? Did we just talk about it? But get used to this notation. We are not going to show these signals ended together like this anymore. This is just one example of how you can do it possibly, but I told you we typically don't do this, okay? There are more complicated approaches for a good reason. So what we typically will do is we will show that you have a load input, which is a signal that controls load operation, and you have clock. Obviously, you need a clock for flip-flops. And the load input will be given in a separate input pin. Notice, CE stands for clock enable, as if this load input is enabling your clock. Does that make sense? Okay, because there are many ways of achieving that. Having a signal that will enable the clock or disable the clock, not just using that simple AND gate. Okay, all right. So get used to this. This is an approach, but not the approach. Okay, so once you set load equals 1, what it does is it takes the output from this tri-state buffer and connects it to the corresponding flip-flop. This is the other flip-flop. Done. There you go. Notice you deactivated the register B and only copied information from register A. Who helped you to achieve that? Tri-state buffer, because you can desensitize some register and use some others. Are you all good? Okay. You might be wondering, okay, what could be a big deal about copying a data from one register to the other register? How many of you have heard about opcode? Right? Some of you, right? Okay. You know, opcodes basically represent different kind of operation that the computer will do. It's part of computer architecture. If you learn machine language, of course, we don't learn machine language anymore. Machines, we were trying to make it as easy as possible for the coders, right? At some point now, you can ask ChatGPT to, hey, write a for loop for me that will do soon. It will give you the code, right? It is so natural now. But there was a time when people used to go down to very close level to the machine language because we simply didn't have these levels of abstractions. Okay? So opcodes are specific binary codes that represent that, hey, imagine you have two numbers. Should I add these two numbers? Should I multiply these two numbers? Should I copy one number? Should I shift by one bit? What should I do? So for different operations, you have a specific code that the computer can recognize and behave accordingly. And when I say a number, another number, where are these numbers? These numbers have to be saved somewhere. And they're saved, surprise, surprise, in registers. Okay? Before an operation, you have to load an opcode to the controller. So loading in a register that you just saw. And you have to save your operands, A and B or C and D, whatever, how many you are dealing with, in different registers. You have register A, B, C, D. And registers are essentially memories. Okay. And then you have to do operations between these two registers. Okay. So note it. And once you calculate something, you have to copy that data over to another register, maybe an output register. Does that make sense? So essentially, all a computer does is copy things from register to register. That's it. You see that? As simple as that. So this thing that you're learning, this is the backbone, and essentially everything that the computer does, copying stuff from one register to the other. As simple as that. It is not hard, honestly. Okay. Can you do it in a more efficient way? That's the big question. Okay. So based on that, now we are going a little bit more serious. Okay. Of course, you cannot deal with one register, one flip-flop, two flip-flop, right? Let's take it a little bit further. So let's consider you have 4 registers, A, B, C, D. 4 registers. Now I'm going to be even more abstracting out my registers. I'm not going to show the clock signal or anything. Assume that it is there. You cannot have flip-flop working without clock, of course. And registers are nothing but, you know, an ensemble of flip-flops. So there is clock, of course, but we don't show the clock. It is so obvious. So you have register A, B, C, D. Always show that there is an enable signal for this register, enable signal for the other register, enable signal for the other register. If you're wondering where is this enable signal going, the previous slide will help you. Notice the enable signal goes to the output buffer, tri-state buffer that is connected to every register. Okay, you have to connect a tri-state buffer with every register's output to make sure you can selectively desensitize it or connect it whenever you need. Are you getting into the habit of abstracting things out now? You see, just to make it look easier, we got rid of the tri-state buffer. We're not going to show it anymore. We are going to assume that it is there inside this box. And we just want to show the signal that we control. We control this enable signal. We control another enable signal. We control another enable signal, another enable signal. Simply by dealing with this enable signal, you can activate one register or multiple register if you want. But remember, when you're sharing a bus, do you guys remember what a bus is? Typically, imagine if I have 16 flip-flops that are sending 16 bits of information to another flip-flop. I will have to draw 16 lines to connect them. You can see it will quickly get exhausting. 16 is nothing essentially. 64, 128, 256. How many lines can you draw? You will lose track of all those lines, right? So we don't typically draw them that way. We just draw one line and say that, hey, it is 16. That means it is essentially 16 lines with 16 bits. It is a data bus. Did we discuss this before in this course? We did. I don't know if you remember this, but just quick reminder, right? So what you're looking at here, for example, this one, it is a bus. And when you see this number with the oblique sign here, it represents it is a bus with 8 bits. It is sending 8 bits of information. So essentially there are 8 lines, right? This is a simplified version again. Okay. So once you have one common data bus, which is this one, and you're trying to send data from different registers, will it be a good idea to activate multiple registers? Folks, what do you think? You're trying to fetch data from this register to eventually some output register. This is a little bit more complicated example. You have more inputs and more output. In the previous example, you had, this is just one register, remember. 2 flip-flops made one register. Here, 2 flip-flop, 1 register. 2 flip-flops, 1 register. So you had 2 input register, 1 output register. Here, we have 4 input registers and multiple, which is like 2, for example, 2 output registers. So we are getting into more complicated territories now. But tell me something. Imagine you activate one of these registers somehow, and it sends its data to the bus. Will it be a good idea to activate another register at the same time and let their data mingle? No, because the data will make no sense at that point, right? 1 and 0 will fight with each other, and we have no idea how things will look like. So you have to make sure by design that only one register sends its data to the output. And you already know about a circuit that ensures only one of them can be activated at a time, not the others. That is our decoder. How many of you remember encoder and decoder? Did we discuss this in the class? Okay. So, and this is again a very simplified boxy representation of a decoder. If you have 0, 0, you activate the first output. If you have 0, 1, you activate the second output. You have 1, 0, you activate the third. You have 1, 1, you activate the fourth. So essentially, based on the combination of input, the decoders will activate just one output at a time. So very simple logic. If you're wondering why would you even need a decoder, maybe because of this. And this is the foundation for computer architecture, essentially. You need to activate registers. Once you enable this register, notice, remember, there is a clock, right? It doesn't happen right away. The clock ensures everything is synchronized. We can keep count. Did the clock edge come? Yes. Okay, now I'm ready to disable the register. Just disable it and enable the next one, and so on. So once the register sends the output, then what? Imagine I just want this output from register A to get to register H. Okay, I don't want the register G to get this input. Okay, how can I do it? Remember, there was another signal called load. With this load controller, if you set it to 0, the register will not load any data, load any input at all. It will just ignore the input, right? Similar to an enable signal. But what is the difference? Enable typically is used with the output, and load is connected with the clock. Are you still with me? Can anybody tell me why I can just simply disable the, just imagine, why can I just not use the enable signal for this register as well? There is an enable signal in every register. But why cannot I just disable this register and just, go ahead with, yes. Yeah, so, but I'm assuming that if they have, even if they have separate enable, in a case where they have separate enable signal that I can control, right? It's not just an invert. That will not really help me unless I take care of this load input. You know why? Because flip-flops will always respond to clock, right? The moment there is a data here, this data will be, please visualize with me. Don't give up. Let's do it together. So this is a register. Inside this register, you have flip-flops. What kind of flip-flop? For the most part, D flip-flop. Where will your inputs be connected? To the D input. Okay? When does the flip-flop send the input to the output? When the clock comes, clock edge comes. So even if you disable the register, it basically represents that its output will not be sent for that cycle. Its output will not be sent. But, as long as you keep your load signal activated, it will still be loaded to the output. It will not be sent to the next level, but it will still be loaded. Because who determines the loading operation? Clock. Okay, does that make sense? So, okay, you can keep it disabled for this cycle, but during the next cycle, when you enable it, it will send the output eventually. Right? So you have to make sure it never even catches on the data. And the only way to disable that input completely would be to desensitize the clock. And who desensitizes the clock? Let's go back to this simple slide here. Remember, if you set load equals 0, your output will always be 0. Doesn't matter what the clock does, right? So essentially, you kind of obliterate the clock by setting the load input as 0. Are you okay? All right. So that's why we use load signal for this output. Imagine you just want to copy this data to H. What you do is you set load for the G register to be 0. So it doesn't load the data. It basically ignores the data. Its output will not be contaminated at all. Only the other register will take in the input and send it to the output at the appropriate clock edge. Okay, so that's how we control data flow in a computer architecture. And as just imagine, just supercharge this vision to millions of components. So you have to keep track of every register. One register sending data to completely different register without being, yes. No, so, okay, don't get me wrong. Load, let me repeat that. Thank you for asking that question, okay? That gives me a chance to clarify. What I didn't say that load is not used, okay? There is a, it is kind of universal that you have a load signal that somehow can desensitize the clock or obliterate the clock. What I tried to say was this simple approach, like, hey, just take an AND gate and the clock with load, done. It is so simple to explain, right? I can just say load equals 0, doesn't matter what the clock is, your output is always going to be 0. It is easy to explain in a class setting, and at this level, it is easy. But there are some practicality concerns, okay? That's why this simple approach doesn't work. We need more circuitry to achieve this. But this load is still used, but not the simple way that you see here. Does that make sense? Okay. All right. Any other questions? Yes.
Ultimately, no, we want the load. Whenever load equals 0, we're going to cancel it by calling out 0.
Exactly. Yes. So the functionality remains exactly as is. When the load is 0, the clock is ignored. When the load is 1, clock is taken into account, right? Okay. Since you, I mean, I don't want to keep you waiting for like years to get this answer. By the time you will forget the question. Let me give you a reason to kind of see why this can be a problem, okay? Imagine for a second that your clock, okay, let me, so it becomes unstable when I zoom in that much. This is your clock signal. It is good to see the problems in engineering, all right? So when your load signal is, let me use a different color. This is your clock signal, and now I'm drawing the load signal. When your load signal is 0, what happens to the clock, folks? 0, right? Like basically clock is desensitized. Okay. Now, interestingly, when I activate the load signal here, notice, what was the clock before? 0. Let me draw the clock response. So this is the output. Let me just write it as clock out. Okay, clock output. So the clock output was 0, but here it will still be 0 because what? Are you paying attention? Because of what? Because the clock was 0. So it will remain 0. And then when the clock is activated, it will be activated and it will follow along. So you have perfectly copied the clock. Does that make sense? Does that make sense? I'll show you the problem here. Ready? Okay. Maybe I will draw on top of it. It will look messy, but it will be easier to understand, I hope. Let me draw on top of the red line. Let's see. Okay. Imagine that you activate the load signal here. You see that, folks? I activate the load signal here. Now what? How will this clock output look like? Which color? Maybe the only color left is black now. So can anybody help me plot clock output now? How will the clock output look like? Let me draw it here. Okay, while the clock load was 0, the clock output will be 0. But when load is activated, it sees that the clock is 1. So it will give you a 1 and it will go on. Does that make sense? Oh, I mean, go on meaning it will follow the clock actually, right? It will follow the clock. But where does it start? It starts when the load is activated and it sees the clock is already activated. So it becomes 1. Are you good? Can anybody tell me the problem here? Is this a real clock edge? There is not a clock edge at this point. The clock was on, but it was on before. The moment you turn on the load, it notices, hey, the clock is on. So there is an edge. But this is a dummy and basically, irrelevant edge. So that will mess up your calculation. So you create incorrect clock edges in certain situations. If you turn on the load signal while the clock is active. So you have to make sure if you're trying to turn on the load signal, you turn it on when the clock is inactive and then let it switch. That way you don't create this random edges. But it is easier said than done, of course, as you can imagine. Okay, so you see the problem here. It's a tangent, but I think it's relatable. You can relate to it. Can you not? Okay, so of course, the more advanced courses you take, the more serious we'll be about these glitches. Glitch minimization is a big thing. There are lectures about glitch minimization and whatnot. Anyways, let's move on to this one. So I hope it makes sense to all of you now that we have a load signal in the register. We have an enable signal, which is connected to the output. We have a clock signal that is routed to all the flip-flops in the register. And I hope now you can understand that, essentially, by the way, see the building blocks. We started with latches. Couple of latches make a flip-flop. Several flip-flops make a register. And several registers can make a system eventually, right? We are going up on the chain. Okay, this slide is interesting to me. I really like it. Oftentimes we kind of undervalue the impact of certain messages. So I try to highlight this quite a bit. Did we see this adder chain before, folks? This is a full adder chain, right? Did we see that before in the class? We did. You did a homework with it. What we didn't see is, hey, I'm giving you a problem where you have to add two numbers, 1101 and 1001. And keep track of the output. So whatever the sum is, you have to add it to another number. So you have to keep track of, it's kind of like an accumulation, right? So you have to keep track of the sum. Let me show you what I mean by this. So imagine using decimal numbers. You are trying to add 12 to 14 to 17 to 39. You're trying to add multiple numbers. So how do you actually do it in hardware? You add these two, save the answer somewhere, and then add that to the other one and save the number somewhere, and then add that to the final one. You don't take all of them simultaneously and just, add them. Does that make sense, folks? In hardware, you either have the capability to add, you basically have capability to add two numbers, just two numbers. But what if you need to add 12? You load one number, you load the other number, add them, save the sum. Load the third number, add it with the sum. Load the fourth number, add it with the sum. Am I making sense? No? Okay. So let me show you in binary what I mean by that. So imagine you have 1101, 1110, 1111, 1010, blah, blah, blah. So you have multiple numbers. Okay. What you do is, this is your number X, this is your number Y. You first load X. Notice, you first load X as input. And then you load Y. And then you add them. You get Z. And now you have to add Z with the next number. So you have to save Z somewhere. Where do you save Z? Did you ever see that feature in the adder circuit? There is no place to save anything. Excuse me. It just gave you two numbers. You add it. You just show the output. Done. As if that's what you need in life. No. Practically, you will be adding many things together. But how do you save the intermediate results? You need something that can hold on to its state. And I hope by now you know flip-flops are good for that. For certain situations, they don't change their output state at all. Okay, so that's why this is a more practical representation of an adder system. This is essentially a parallel adder with accumulator. It is a mouthful. It sounds like a lot, but the phenomena that I told you, add two numbers, save the output somewhere, and then add it. This is called accumulation, basically. You just keep, accumulating the output, the sum, and add it to the next one. That's all. It is accumulation. Yes.
So are all the flip-flops considered one register?
No, that's a good question. So this is shown in a lower granularity. We are not using registers here. These are individual flip-flops. Okay, they are individual flip-flops. So they are connected very close to the adder block. Remember, each adder can deal with one bit, just one bit. But registers don't deal with one bit. Registers deal with multiple bits, right? So you don't need a register here. You need a flip-flop. You know who else deals with one bit? A flip-flop. So with one full adder block, you have one flip-flop, because that is good enough to save that one bit. Are you good? When you add a binary bit with another binary bit, you need to save its sum and also carry, but sum mostly. Okay, now this is gonna be difficult to understand reading from a textbook, trust me, because I get confused when I try to read these things, right? So please try to pay attention, and I believe it will be super easy for you to make sense of it later on, okay? I will start when you're ready. Ready? Okay, let's do it. So without any loss of generality, we just look at one bit here, and then we repeat the approach for everything else. It's essentially a ripple carry adder. You have two inputs, X and Y, and your output is sum and carry, as you know. So in a ripple carry adder, carry is sent to the next adder block, and the next adder block, and the next adder block, and the next adder block. Okay? So imagine I'm trying to add a few binary, 1001, 1110, 1111. These three numbers. For the sake of simplicity, let's take three numbers. How do I start? Notice, I start with putting the first number. Folks, notice, let's zoom into this one. One of the input, typically you have seen in an adder, X and Y as inputs. But in this circuit, you're seeing that Y is the only input, and X is coming from the flip-flop output. So you don't control the flip-flop output externally. You don't have any control over that. You see my point here? Can you just put in a random bit at X? No, because it is a flip-flop output. So you have to somehow control the flip-flop to send the output, essentially, right? Now, the only input that you have control over is this, just one. So how do you get X into the other end? And okay, forget about X and Y. Take numbers 1, 101, 1110, 1111. Okay, so I want to first load this number 1101. What should I do? Let me show you. So I will set this 1, 1, 0, 1. Okay, this input. This is Y, but I'm gonna set X equals Y. You see my point here? 1101. Okay, once you do it, what was your carry? It is 0. What is the other X? Do you know? Like adder will need two inputs. How will the adder know what X is? Notice there is a clear input for the flip-flops, which will clear the flip-flop. What do I mean by clearing the flip-flop? What will be the output of the flip-flop when you clear it? 0. So to begin with, we clear the flip-flops and we load the first number as Y. So what do you get here? The output will be 0, 0, 0, 0, 0. As if X is always 0, 0, 0, 0. Will it change anything if you add something to 0, 0, 0, 0? No. So after the adder goes through the addition, it essentially adds 0 to all the other bits. So your output will be what? Can anybody tell me what the output will be? So whatever the input you provided, 1, 1, 0, 1, that will now become the output 1, 1, 0, 1 for the sum, right? You guys all agree with it? So you essentially copied your input to the sum output, right? Your sum is essentially representing the input because the other input is 0. So now notice your sum is not independent. It is being fed to the D port of the flip-flop. So it is being fed as a data to the flip-flop. So the flip-flop will get 1, 1, 0, 1 as its input. And when you provide the clock edge, next clock edge, it will send it to the output. So your output will now become what? 1, 1, 0, 1. 1. So with that many steps, you have managed to send X to where it belongs. Does that make sense? So all that hard work to set the value of X. And I haven't even set the value of Y now. So do you see that X is set now? You start with providing X and clearing the flip-flop so that the sum is itself X, and you you send this input to X. So you have 1, 1, 0, 1 here. So, oh, I forgot 1, 1, 0, 1. Maybe the next number is 1, 1, 1, 0. Okay. So how can you send this number to Y? Basically, you just set it 1, 1, 1, 0. So the second number is easy. The first number is tricky. You have to reset the flip-flop, set it as Y, and Y will be sent to X eventually. So Y is free now. So now you can set Y to whatever it should be, really. So this is X, this is Y. Are you good so far? Let me also draw Z. Maybe Z it would be 1, 1, 1, 1. Okay, and this is Z. I'm gonna need to add Z essentially to this. But let's see. Once you set Y1 and X1, wouldn't the adder work? The adder will add X1 and Y1, X2 and Y2, X3 and Y3, and all of them, and give me a sum. And that sum would be the sum of what? These two numbers. Are you good so far? So you get these two, the sum of these two numbers here. And notice this sum is being fed as the input to the flip-flop directly. So what will appear here, folks? Can anybody tell me what will appear here at the output? The output will be, let me erase this a little bit. The output will essentially be this sum. Sum of what? X and Y. So X and Y, the sum of X and Y is now your new input. You see that, folks? It is now your new input. So if I provide the third number, which is 1, 1, 1, 1 here now, 1, 1, 1, 1, you will be adding this number to the sum of the previous two automatically. You see my point? If you have a fourth number, just repeat the process. So that's how you can keep accumulating. And eventually when you're done, the final output will give you the sum of everything, not just two numbers. You appear very silent. So you either got everything or nothing. Okay, be honest. How many of you didn't get it? There is nothing, to worry about. All of you got it? No, okay. I see that some of you didn't get it. It's fine. Don't worry. Let me quickly repeat it. Even for the people who got it, hopefully it will be good revision. So here we go. So we have full adder. We have an adder chain. Typically, we just have the carry out going from one level to the other and done. And we provide X and Y, right? We provide X and Y as input. But that is not really usable in a situation where you have multiple numbers needed to be added, right? How can you add like 5 binary numbers? No, you cannot. You just add 2 numbers with an adder block. So there has to be a way. And this is an easy way. So now, when we went over the adder circuit, we didn't learn about sequential logic. So you didn't know about flip-flop. So I couldn't show you the practical design. I just showed you a very simple design and nobody asked me. See, you never asked me, what if I try to add 3 numbers, 4 numbers? How is it done? Okay. This is an example of how it can be done. You take the sum of the adder and put it as an input to a flip-flop. And you do it for every stage, obviously. Whatever you do for one bit, you do it for the other bits as well. Okay? So imagine you're trying to add 3 numbers, 1101, 1110, 1111. How can I load the first number? I start with setting 1101 to the input Y. Okay? And my carry input is 0. And I clear, using the clear signal, I clear my flip-flops. That means my flip-flop outputs are all 0, 0, 0, 0 to begin with. So notice flip-flop output is basically the input X. So what is your input X? 0, 0, 0, 0. What is your input Y? 1, 1, 0, 1. What will be the sum? 1, 1, 0, 1, essentially, right? Does that make sense? So your sum will be 1, 1, 0, 1. But then notice this sum is directly being fed as the data input to the flip-flop. So when the clock edge comes, the flip-flop will take this input and send it where? Send it to its output. So this will become 1, this will become 1, this will become 0, and this is 1. So notice now your input X has found its right place. Now X is at the X input, right? You have to do a dummy add to send it to the appropriate input. How about the next number? For the next number, you are ready now. You are just gonna set them to, say, the next number is 1, 1, 1, 0. Set them to 1, 1, 1, 0. So now you're ready with both X and Y. Okay, you have X already set up, you have Y input, and now they will be added together, and the sum that you will get, this is gonna get messy, but you'll get a sum, right? You'll get a sum, and that sum will directly be fed to the flip-flop, and the flip-flop will send it to its output. So what does the flip-flop output contain now? The flip-flop output contains the sum of the first two numbers. Does that make sense? Okay, now what if I load the third number? 1, 1, 1, 1. This third number will be added to the sum of the previous two numbers. See that? And I can keep repeating the process. I will keep loading one number at a time at this input, and the feedback loop will make sure it is accumulated. So there you go. You can add as many numbers as you want using the same circuit. So when you bring in sequential logic and combinational logic together, the system becomes powerful. Just imagine before invention or discovery or the thinking about the sequential logic approach, our Boolean logic was not really that powerful, right? It would be messy to deal with stuff like this. So do you appreciate it now, folks? The flip-flops are useful. Okay. All right. We have 1 minute, so I'll not go to the next slide. This is good because there's a very different topic, shift register. We'll start with shift registers in the next class. All right. Have a great weekend.